Okay, good afternoon. So the next part of the lesson, geometry, is actually a rather technical lesson, so you have to listen carefully, and then there are a little bit harder exercises in the book related to this topic. And that's the notion of similar triangles, okay? So what do we mean by two triangles to be similar? So similar is different from identical, or what we learn later as congruent triangles. Similar means that if I have two triangles, for example, it's hard for me to draw them precisely, but I hope that I can give you the idea. So I have a triangle ABC, and I have another triangle, which is probably the smaller version of that triangle, so I will call it A prime, B prime, C prime. I would say that these two triangles are said to be similar, and I use this symbol for that. I would say triangle ABC, I use this symbol, similar to the triangle A prime, B prime, C prime. What do I mean when I say two triangles are similar? It means that all the corresponding angles are equal. So in this case, angle A is exactly equal to angle A prime, angle B is exactly equal to angle B prime, angle C is exactly equal to angle C prime, okay? But more than that, I want to have the ratio of corresponding sides to be exactly the same. So it means that, for example, if I take AB, the length of AB, and divide it by the length of the corresponding side from the other triangle, in this case A prime, B prime, it doesn't matter how I calculate their ratio. If I calculate the ratio using this side, or I use it the other side, AC over A prime, C prime, or BC over B prime, C prime, these three fractions, these three ratios are the same. Yes? So when I say that two triangles are similar, it means that they are satisfying 5 conditions. 3 conditions for equality of the angles, and 2 equalities for the ratio of corresponding sides. Yes, so that's the meaning or definition of two triangles to be similar. I don't know, for example, you can take a photo from it and zoom out or zoom in what you are making. You are making similar triangles from the original one, yes? So you're rescaling it without changing the angle. So you are changing the size, but you are not touching the angle. So the angles remain the same, but the triangle becomes bigger or smaller. But the triangles are called similar in that term. Yes, please?
Isn't this same as being identical or?
No, there is no word identical. The terminology in the geometry we use is called congruent, but that's exactly what you mean as identical. It means that they are exactly carbon copy of two triangles, the same triangle. Yes? So there are 2 different words, but I don't know, in some reason, in Swedish books they are teaching it in different way, because I would prefer to teach congruency first and then similarity. But because they are not going to prove any of these things to you, it doesn't matter in which order they present them. Yes?
So wait, are you saying that the triangles can't be identical at all because
No, they can't. No, identical means exactly the same thing, yes?
Yeah, because there are equilateral triangles.
Yes.
So.
But equilateral triangles, one of them can be smaller, the other one can be bigger, yes? They are not identical, yes? But equilateral triangles are all similar, yes? So I just want you to know, for the time being, I am defining this word for you. It's a geometrical terminology term that you need to learn. When you say that two triangles are similar, they might be exactly of the same size and of the same angles, everything. You can see that that's possible. But that is not the main definition. And so the definition is, when you say that two triangles are similar, it means that the angles from one triangle are equal to corresponding angles of the other triangle, but not just that, the sides are proportional. So it means that if you take the length of this side and then divide it by the length of the corresponding side here, you get a number. It doesn't matter with which one of these sides you are doing this, you would get the same thing. So that is the meaning of similar triangles. If you have these conditions all satisfied, then you say that I have two similar triangles. And that is the symbol that you use to show that these two triangles are similar. Yes? Is that clear? So in principle, if I ask you to show that two triangles are similar, you have to check 5 conditions. You have to show me that the angles are all equal. You have to show me that this fraction and that fraction and that fraction are all equal. But it turns out that you really don't need to check all of them. For example, it is clear. Do I really need to check equality of 3 angles? It's clear not. Because, for example, if I check angle A and I realize that angle A is equal to angle A prime, and I check that angle B is equal to angle B prime, automatically the third condition is met, yes? Because the sum of the interior angles should be 180 for each one of them. If a pair of them are equal, so the third one is also equal. So I really don't need to check the other one. Okay, so there are 3 theorems, 2 of them mentioned in the book without proof. So you have, of course, in my Olympiad lessons, I will cover them to see why they are correct. But for the time being, you just use them, okay? So there are 2 theorems that you want to use. You are allowed to use them to prove that 2 triangles are congruent. Okay, but before doing that, let me, for example, solve this problem from the book, okay? So they have given you 2 triangles. So one triangle here. They have mentioned that this one is 34 degrees and this one is 75 degrees. And then they have drawn another one which is slightly bigger. Okay, I will try to do good. So here. And then they have given you, this is 75 degrees and this is 71 degrees. And the name of this triangle is EFD. And the name of this triangle is BAC. Okay, so for example here, you want to see if these 2 triangles are congruent or, are similar or not. Okay, so you see that one angle here is 75 and one angle here is also 75. One angle here is given to be 34 degrees, but one angle here is given to be 71 degrees. I want to see if these 2 triangles are similar or not. So what I'm supposed to do, in principle, I have to calculate the third angle to see if all angles are equal. So for example here, if I want to calculate this angle, this becomes what? 180 minus 34 degrees and minus 75 degrees. If I calculate this integral, what will happen? Sorry, this angle, what happens? This becomes 109, am I right? This becomes 109, and I subtract it from here, it becomes 71 degrees. So this means that this angle is 71 degrees now. And I calculate the other triangle, this angle here, then it is clear what angle will be this, yes? So the angle D is equal to what? 180 minus 71 degrees minus 75 degrees, yes? If you calculate this number, it turns out to be how much? 34 degrees. So this means that this angle is also 34 degrees. But be careful that right now I know that all the angles of this triangle are correspondingly equal to the angles of that triangle. But that is not on its own enough in general to conclude that these 2 triangles are similar. Why? because I haven't really checked, I do not have any information regarding the lengths of these sides, yes. In principle, I have to take the length of this and then divide by the length of this and write it down somewhere. And I do the same thing for this one and that one, and do the same thing for this one and this one, and compare these three numbers, or these three numbers should be exactly equal. If that is the case, then because the angles are also the same, I can conclude that the triangles are similar. Okay? This is in principle. But it turns out to be that it is not necessary. Okay? This is I want you to remember, because this is not in the formula sheet, you need to remember it. There is a theorem that guarantees that you don't need to be so detailed about checking this. Only two angles and two angles. If two angles of one triangle are equal to two angles of another triangle, you don't need to check the third angle, which is of course trivial, and you don't even need to check the equality of these fractions. They have to be the same. It turns out to be the same. Okay? Is that clear? So the first thing that I want you to say for similarity, which of course is not trivial at all. You see, here we calculated the angles. You see that all the three angles are equal. But there is no guarantee, I hope that you see that this is not trivial at all, that y, if the angles are all equal, then the ratio of the sides are also equal. This is not clear, and this is not mentioned in your book, the proof, okay? But I just want you to know that. So similarity theorems, there are two of them. One of them, which is the most famous one, and we usually use this one, is called angle-angle theorem. If I want to simplify it. What do I mean? I don't write it down, I just talk about this orally, but that is the meaning. It means that if two angles from one triangle are equal to two angles of the other triangle, it is guaranteed that these two triangles are similar, even if you don't check the other conditions. The other conditions can be shown that they are automatically satisfied. Is that clear? Okay. So, the next theorem is also very interesting and not trivial. It tells you that you don't need to even check the angles. If you just check the equality of these, this is enough. Because if this is to be true, then these three conditions are also automatically met. Which is of course not trivial, you see? Because if I know the equality of two angles, of course the third equality is more or less evident. But we don't know if the angles are correspondingly equal, why that is enough to show that the ratio of the sides are also equal, and the other way around. If I just know that the ratio of sides are equal, how can I understand that definitely the angles should be also equal? But as I told you that these are not discussed in the book, they just want you to know about this, okay? So I would say that if just AB over AB prime, A prime B prime is equal to AC over A prime C prime is equal to BC over B prime C prime, so that is just enough. You don't need to check the angles, that the triangle ABC is similar to the triangle A prime B prime C prime. So these two pieces of information, it's important to know here, even though I know that this is a little bit artificial. So if you are interested to see why this is the case, you have to be patient, so that when in Olympiad lessons I reach these parts, I will teach that why this is true. But for the time being, you just take them for granted and then you'll use them. First of all, tell me, is that understandable? Okay, so now let us go back to this problem. Do you think, according to the pieces of information that I had, the blue ones were the ones that I added, but before the blue ones, can I just, by looking at the information given to me, can I conclude that these two triangles are similar? Yes or no?
Yes.
Why?
Because we do this process that you did in our head.
Yes, and then I found all the angles. And then I see that, for example, 34 here and 34 here are equal, one angle. 75 here and 75 there are equal. So according to angle theorem, these two triangles should be similar. Is that understandable? I mean that it is, I'm sure that probably if you are very interested in understanding things, this is not very clear why I just check two angles automatically. This is also satisfied, but you have to wait on it. So just learn how to use it. And whenever you want to use them in the exam, you have to mention them. For example, if you're using angle theorem, you just mention that I am using the angle theorem. Okay, and now let me solve this problem also from the book. So they have drawn two triangles for you here. One a little bit smaller, the other one a little bit bigger. Okay, so if I can draw this. This is 13. So let us assume that everything is expressed in centimeters. And then I have 11 here. And then this length is given to be A, which we don't know. And then I have another triangle. Yes, a little bit might be bigger. I have to draw. Yes, but of course I cannot draw very good pictures, precise pictures. Okay, so for example like this, and they have given you this is B, and then this is 16.5, 21, and then they have mentioned that this angle is equal to this angle, and they have also mentioned that this angle is equal to that angle. Okay? And they have asked you to calculate the values for A and B. Okay? So when you look at the picture, first of all, even if sometimes, by the way, in geometry questions, it is very common that they say that the picture is not to scale. So it means that you are not allowed to just guess what is happening in the picture. You have to have a reason for that, okay? So, by looking at this picture, what I understand, this is the standard convention. When you see one, I don't know, one of these arcs here, one arc here, it means that they are telling you that these two angles are the same. And if you see two arcs here and two arcs there, it means that they are telling you that these two angles are the same. Okay? And then they are asking you to find that A, which is missing, that B, which is missing, based on the information provided for you here. So, for example, let me call this triangle ABC, and let me call this triangle E. So D, E, F, yes, like this. So first, if you want to use similarity, you have to convince the person who is reading your answers that these two triangles are similar. You cannot just say that, okay, let us assume that they are similar. Okay, but of course, everything is clear. Why these two triangles are similar? So you should say that based on angle theorem, these two triangles are similar because two angles of one triangle are equal to two angles of the other triangle. But the point is that they haven't asked you about angles. They have asked you about the lengths of two sides. If you know that, so I would say that angle C, let me write it properly. I would say that angle C is equal to angle F because you told me. Angle B is equal to angle E because you told me. Then I would say that, okay, angle theorem, you can just simply write like this. Angle theorem tells me that the triangle ACB is similar to the triangle DFE. Okay? When I now know that the triangles are similar, I can write the ratio. I can say that, okay, now that I know that the triangles are similar, it means that the ratio of corresponding sides are all equal. So this means that the ratio of AC to DF is equal to the ratio of AB to DE is equal to the ratio of BC to EF. Yes, is that understandable? So I mean that you cannot just start writing this in the exam. You have to tell me why you are allowed to write this. You are allowed to write this if you know that these two triangles are similar. But how do you know that? You are using one of these theorems, angle-angle theorem. Yes. So this is a good way of writing this in the exam. Okay, and then what happens? I use the information given in the problem. Instead of AC, I can write 11. Instead of DF, I can write 6,5 equals to. Instead of AB, I don't have it, but they have asked me to consider it to be A. And then divided by DE, you see in the picture it is 21. And on the other side, BC is 13. Divided by EF, which is given to B. And now it becomes very simple. So when you say that these fractions are equal, of course there is no help if I take these two. Of course doesn't mean that this is wrong, but if I take these two, then I have one equality, but I have two unknowns involved. So that's not a good choice. So a good choice is that take these two together once, and find A, and once you found A, you can take these two to find B, or if you want from the beginning, you can take these two to find B. It doesn't matter, yes? For example, let me just concentrate here on this bit. And that's also, by the way, very important. I just want you to know that whenever you have this type of fraction equals to another fraction, this means that this product is equal to that product, yes? So this means that 16,5 times A is equal to 21 multiplied by 11. And then you are supposed to find A, so you have to make A alone, so you divide everything by 16,5. So what is that number? It is 2, 3, 1, yes. And then divided by 16,5. And if everything, of course, I think, okay, it's expressed in centimeters, so that is centimeters. So if you want, you can put this in the calculator to get some value for A, but we don't need to spend some time on it. Okay, after this is found, I will take this one and that one and to find B. So what happens here, then again, we can just simply ignore the middle one. 11 times B is equal to 13 times that number, 16,5. And then because you want to make B alone, so let me write times 16,5 and then divided by 11. Okay, but by the way, let me just, because this is given in the book.
The fraction is exactly equal to 14.
Which one? This one?
Yes.
Okay, so that is exactly to 14, thank you very much. And the other one, can you also calculate that one roughly? So that's exactly equal to 14 centimeters. This one? 13 times 16,5 divided by 11.
19.5.
19.5 centimeters. So these are the numbers for these triangles. So that's a very simple problem, but I think it's a good problem. Any questions? Okay, let us try to solve some more interesting problems. So another problem that I want to talk about today, which is extremely important. First of all, let me ask your opinion about this. I have a right angle triangle from the beginning. Yes. This is, by the way, is a very famous problem. I want you to understand that and then somehow send it to your memory, okay? So I have a right angle triangle here. But what I do, I draw an altitude for this. Altitude for the hypotenuse. What does it mean? It means that I just drop a perpendicular line from A to BC, okay? So I will drop this one. Okay, so I will have this, I will call it H here. So by dropping this altitude, the real name is altitude, the length is height, okay? Okay, so by dropping this altitude, I will get 3 triangles, 2 small ones and one big one. All of them are of the same type. They are all right angle triangles. I had my right angle triangle from the beginning, so it was a one right angle triangle. Then when I drop this perpendicular line, of course this one is 90, the other one is also 90, so this triangle in its own is a right angle triangle, and this triangle in its own is a right angle triangle. So the one thing that I want you to convince me of, I want to give you time to tell me why, all these triangles are similar. So remember this, but why is that? So my claim, so here we claim this. We claim that this triangle, I don't know, ABH is similar to the triangle so ABH is similar to the triangle ACH, and it is also similar to the triangle that I started with. Yes, so that is what I want you first tell me why this is true, and then remember it. And now we will see that there are some interesting things that we can get from this. Might be interesting for you as well. Okay, so for example, let us concentrate on 2 things. I don't know, might be, let me tell me why this small one, I think that's good. Why this small one here is similar to the biggest one, to the bigger one, to the original one. So but when I ask you this, you need to think about 2 things. Either you should convince me 2 angles from one are equal to 2 angles from the other one, or you should convince me that the ratio of the sides are equal. Yes? Which one is more suitable for this picture? So if you want, I can also draw them outside of each other so that you are not confused. So these are the things that you can help yourself with. That's, I don't know how you want to help yourself with. So I can draw this outside. Yes. So this is A, BH. You can visualize it. Yes. BAH. And what I had before was this bigger one. Yeah. Something like this. I don't know. I am just bringing them out. So this is again A. It's not a good picture, but hopefully you understand what I mean, yes? So this one, I drew it separately to visualize it better, and then I just copy and paste the bigger one here, okay? Now, can you tell me why 2 angles of this triangle are equal to 2 angles of that triangle? Yes, Tim?
Yes, when you draw the vertical,
yes,
perpendicular to the BC line,
mm-hmm.
You create a 90-degree angle.
Yes, so you are saying that this is, if I call it H1 here,
yes.
This H1 you see is 90, and this original one is also 90. So one angle of this is equal to one angle of that. And then
B stays the same.
So B is staying the same, exactly. So this, I've just put them outside, but this is just the same angle, yes? This angle that you see here plays the role of one angle of this. On the other hand, it is also an angle of the bigger one. That's it. 2 angles of one triangle are equal to 2 angles of the other triangle. So this B and B are exactly the same. You see, don't get confused. I put them outside of each other, but they are exactly the same angle. And then one angle is 90, the other bigger one is also 90. So 2 angles of this triangle are equal to 2 angles of this triangle. They are similar. Yes?
Yes.
Okay. But now, For the same reason, I hope that you agree with me, this triangle is also similar to the bigger one, because that's essentially the same thing from the right hand side, yes? So if you want to, I can just draw this bigger one here. So this is also, you can imagine like this, yes? So I don't know, this is A, H, C. Can I repeat the same argument? Yes. If I call this one H2, which is here, is 90, so the original one is also 90, but then I can repeat this. This angle C is not only an angle for this one, but also an angle for the bigger one. So this is actually the same as this one. So two angles of this triangle are also similar to two angles of this triangle, yes? So this means that this one is similar to this one is also similar to that. Can I conclude that they themselves are also similar? We haven't proven these things in detail, but the answer is yes. But let me try to ask you another question. If I have asked you to convince me of similarity of these two without this method. So in this method, I showed to you that this triangle is similar to the original one. And I also showed that this one is similar to the original one. Then I concluded correctly, of course, that these two triangles that are similar to the same triangle are also similar to each other. That's also true. I haven't talked about these things in detail, but these are also true. But could I do it without this? Could I say this, so without going through the bigger one, can I convince myself that this triangle is similar to this triangle without showing that they are similar to this and then consequently they are similar to themselves? How can I do that? Why do you think that one on the left is similar to the one on the right? And now I clean this one so that you don't see this middle one. Again, one thing is very, very clear. What is that? This H1 is 90. H2 is also 90. At least one angle from here is equal to one angle from there. But what about the other angle? Can you say something about the other triangle? Sorry, about the other angle. So let me give you hints. So here I call it A1, and here I call this one A2. You go back to this picture, A1 is here, A2 is here. Tell me why B is equal to A2. B is equal to A2, C is equal to A1. Why? It's very, very simple. Look here, A1, A2, you know something about A1 and A2, yes?
A1 and 2 is 90 degrees.
Yes.
Therefore, B and C is 90 degrees.
Yes, B plus C is 90 degrees. Yes.
And then...
That's correct, that's correct. Why do you hesitate? Say, you see, so B, no, let me write. B, this B plus this A1, everyone, what is the answer?
90.
That is 90, yes? Because the sum of three angles should be how much?
180.
180. But this B plus A1, so it becomes 90 degrees. Agree? Yes? Okay. And now B, A2 plus A1 is how much? A2 plus A1 in the original picture is also 90. Yes? So if this sum is 90, this sum is also 90, this means this sum and this sum are equal. Yeah? So this means that B plus A1 is equal to A2 plus A1. Okay, but A1 and A1 are the same, so I move one of them to the other side, it becomes negative of that one, it's cancelled. So it means what is left is B equals to A2. So I showed that B, what you said here, you see here, is equal to A2. Yes? Is that clear for everyone? Okay. So then, of course, the other one is also clear. So this triangle is congruent to that, similar to that triangle. We proved them directly. But let me ask you one more question here. Now that we are sure that these two are similar, can you write me the correct way of writing the ratios? So you know that when I want to write the ratios, there are sometimes I see students make mistakes here. So I would say that, okay, tell me, what should I write in the numerators here? What should I write in the denominators here for this triangle and that triangle? Now I am sure that these two triangles are similar. So when I know that they are similar, I am allowed to write that ratio. Okay? And that is up to you. You want to choose the numerators for this one, the denominators for that one, or vice versa. That's up to you, it doesn't matter. But you need to respect the order that you choose from the beginning. Okay? So for example, on the left hand, let me write this one, the sides of this one on the numerator. So I have three sides that I have to consider, yes? One side is AB, I would write it here. Another side that I want to consider is AH. Another one that I want to consider is BH. So of course this is not, you can replace them. There is no reason that you have to respect my order. But you should be organized in writing the ratios, otherwise it would be a mess. But in the numerator you have a lot of freedoms, you can arrange them in any way that you like, but as soon as you decided about the order of the numerators, then there is no freedom in the denominators. You have to respect the order that you have already chosen. And I want to wait for you, okay? So can you tell me, if I have chosen AB as the numerator of the first one, what should I choose for the denominator of the first one?
AC.
Yes. Can you understand that? Yes. So in your head, you need to rotate it somehow so that equal angles match, and then you have to write the erosion. So for example, don't get confused to write AB over AH. No, that's wrong. Yes. So in my head, that's one way. You just rotate it in your head so that this angle, which is equal to this angle, goes up. This angle, which automatically becomes equal to this angle, goes to the right, and then this becomes exactly more or less the same location. And then you have to start writing. So in that case, if you imagine that, what will happen? If I have written AB on top, then AB will correspond to which one? AC. Then I have to write AC here. This is a have to. Okay? And then what happens? Can you tell me, if I have written AH there, what should I write?
HC.
HC or CH, doesn't matter, HC. And then of course it is clear that when I have chosen to write BH there, it becomes what? AH, yes? So that is something, some skill that you have to learn, okay? Okay. So to check your understanding, let me go back and write the other ratio for this small triangle and the original one. Can you do that for me? So for the bigger one, I keep the smaller one as it is. So I would write AB, I would write AH, I would write BH. But this time, we also learned that this triangle is similar to the bigger one. Can you do these rotations or whatever you want to do in your head and write tell me what should I write in the denominators? The denominators are the sides of the bigger one this time. Yes, Sergey?
BC.
So let me check. I have to check myself. AB, yes, you say BC. I agree with you. And AH,
AC.
AC, yes. And BH,
BA.
BH AP. Yes, that's correct. Everyone agrees or needs explanation? Do you need explanation here? Yes or no? Understandable? Okay, so let me test your understanding once more. We also learned that this triangle is similar to the bigger one. Okay, but now let me write these sides on top. Let me side this time, I don't know, let me just keep the order. So AC, I am just writing this triangle. AC, CH, and then what? AC, CH, and AH. Okay, I want someone else tells me. So what should I write here for the bigger triangle? When I write AC for this smaller one on the right, what should I write from the bigger one? Yes?
BC.
BC. Thank you. And then CH, what should I write?
AC.
So let me check myself. Yes, AC. And then the last one is what is that last one?
AB.
AB. So is that understandable? So it is something that you need to learn. Because most of the exercises that you get in the book, they have written in a nice way. For example, if they have given you this, they have also given you this. Okay? But if the problem is a little bit harder, you have to imagine it yourself so that you can do it. Okay? But in principle, if you want to understand it better, there is a definition. What do I mean by corresponding sides? I mean the sides that are opposite to the equal angles. Yes? For example, here, which one was that? This one was which one? AC. Okay, this one was this one and that one. Okay? So what I do, if I have chosen AB from here, I would say that AB is opposite to the 90-degree angle here. I go here and find the 90-degree angle here and read the opposite one, which is AC. So this is why I put AC here. It's another way, but I think this is more formal way of doing it. I would myself prefer to imagine it quickly, okay? For example, I have written AH here on the second fraction on top. AH is opposite to B. But I learned that B is equal to A2. Opposite to A2 is CH or HC. This is why you see HC appears in the second. So if you want to do it formally, you have to convince yourself which angles are equal and then write them down, okay? But I think if you have a little bit of imagination, it's much simpler. Yes? Okay, but by the way, let us explore the consequences there. Those are also very interesting ones. So for example, it's a very, very nice thing I want you to remember in a right angle triangle. Let us see what happens here, by the way. Of course, this is also equal to them, but forget about them. I don't need that piece of information. I want to focus here. Then AH times AH is equal to what? Is equal to BH times HC. Yes? But that's a very nice property of right angle triangles. Probably you didn't know before that, but it is also good to remember. AH times AH is AH squared, and this one is BH times HC. So I myself have it in my memory. This is a very nice relation for a right angle triangle. By the way, let us see what we proved, which was not possible before knowing this topic. Yes? So what we showed is that if I have a right angle triangle, and if I draw the altitude for the hypotenuse, it will divide the hypotenuse into two parts. And interestingly, if I take the lengths of these two and multiply them, it becomes the length of the height squared. Okay, it's very nice, yes, isn't it? The length of AH to power 2 is equal to the product of those two pieces, which we didn't know about this, and we were not able to get it using Pythagoras theorem. So that's a really new thing we learned, yes? Is that understandable? Okay. So that is, I have it in my memory because you don't have to, but that is something it's good to know. Might be, in the exam, they give you and ask you to prove this. If you want to prove this, you should say that, okay, I prove that these two triangles are similar according to what we explained. And then using that, you can write this part, and then from this part, you can conclude this. That is one type of exam question. Okay, let us also explore the other one. So here, you see, let us ignore the middle one this time, and let us concentrate on this one and that one. And let us see another interesting thing happens, yes? AB times AB becomes what? Let me write this. AB times AB is equal to, what happens? BC times BH. Or let me write BH times BC. But AB times AB is nothing except that AB squared is equal to BH times BC. That is also a nice relation that I have it in my memory, but you don't have to. Let us just interpret it on this picture. So this tells you that if you are interested in this side squared, AB squared, you can take the hypotenuse BC and multiply it by BH. How can I interpret BH? BH is called, for example, the length of the shadow of AB on the hypotenuse. So if you shed light from above, this would be the length of the shadow, which is called the projection. The projection of AB on the hypotenuse is BH. So if you take the shadow of this side on the hypotenuse and multiply it by the total hypotenuse, you will get this length squared. Yes? Okay, let us investigate what will happen here. This time, let me take these two. I multiply AC by AC, and then I multiply CH by BC. Of course, that is, because by the way, it seems that nature doesn't distinguish between left and right somehow. Yes, of course, this is not correct, because in physics it happens that we have a violation of parity. So it means that somehow nature distinguishes between left and right somehow. But here, for the time being, in the world of elementary particles might be the case. But here we have this scenario. This is the same scenario. This triangle is on the left. This is more or less the same triangle on the right. So if something is true for the left one, it should probably be also true for the right one. Yes, it's more or less the same thing. It's not symmetric, of course. This one is bigger than this one. But this is the matter of left and right. The left side of AH, the right side of AH. So it means that if you have this one for the left one, you should probably expect to have something more or less the same from the right side. And you will have it. You see AC times AC is CH times BC. And then this means that AC squared is equal to CH times BC. And then you see the interpretation is exactly the same. So if you take the hypotenuse, which is BC, and multiply it by this shadow, by the shadow of this on the hypotenuse, which this time is CH, and if you multiply the shadow by the total hypotenuse, you will get this one squared. Yes, is that understandable? Okay, but there is also a nice property coming in. You have to be ready for that. Let us add these two to see what happens. Yes, just to explore. So what I do, I would say that AB squared plus AC squared is equal to. I was able to show that this is true. I was able to show that this is true. So I add the left-hand sides. Then, if I want to respect the equality, I have to also add the right-hand sides. So this becomes BH times BC plus CH times BC. Yes? But what happens? On the right-hand side, BC is in common. I can factor it out. So I can put BC out. From here, BH is left. From here, CH is left. But look at the picture now. What is BH plus CH? Can you write something for it? BH plus CH is BC. So instead of this one, I can write BC. Yes? So this becomes BC multiplied by BC. But instead of BC multiplied by BC, I can write what? And then what do you see? This is a proof for Pythagoras theorem. Yes? So we were able to show that AB squared plus AC squared is BC squared using similarity ideas. Yes. Yes.
So there are two proofs for Pythagoras.
Hundreds of proofs.
Hundreds.
I think this is the most famous theorem in mathematics. I think you can Google it around. I think more than 100 proofs you can find proofs. Yes? Okay, so what you see is that these similarity arguments are actually nice, and the problems related to similarities could be really, really tough to understand. So, for example, realizing which triangles are similar are not that usually easy. Yes?
370 proofs.
100?
370.
370 proofs, yes. Okay, I mean that's much more than this, but at least this is one way to prove the Pythagoras theorem. Any questions? Okay. There is a problem I see here. I don't know the exact translation, but I think this is a little bit tempting for me to see how it goes, okay? Problem 5035. Okay, can one of you read that problem and then see what is going on? Try to solve it together, okay? I haven't seen that before, but it is a little bit tempting, you know, because of the relationship. It's written there. 5035. I myself might understand probably a little bit enough for solving the problem. So let me translate it myself. If you don't agree with me, just tell me. Okay, so we draw a right angle triangle ABC. Okay, they haven't mentioned which one is 90 degrees, have they? That is a little bit strange. Haven't they mentioned which one is 90 degrees? Okay, so let me translate. It might be that would be a better idea. So if you know, just read and try to solve the problem yourself, so that I just do the translation. Okay, sorry. So in the book that I have, it is 535, but in the electronic version that you see, you have two more problems. So, and then they have double the star it. In my book, there are no stars for it. Okay, so it is 5037 in your digital book. So let me change it to the digital one. It's 5037. With two stars. Let us see, can we solve the problem? It seems to be nice, yes. Okay, now I will try to translate it.
The right angle be angle C, since the hypotenuse is AB.
Is it mentioned?
Yes.
Ah, yes. Okay, thank you. So draw a right angle triangle ABC. From the corner C, drag, this is the translation here, drag a bisector to point D on the hypotenuse AB. Yes. So let me at least, I don't know in which direction, let me just draw it in that way. So as usual, as I did it here. So I will take this one. So Tim is right 100% here, but this should be C, definitely, because they mentioned that the hypotenuse is AB. Okay, that's good. And then from the corner C, or vertex C, is the translation, drag a bisector to point D on the hypotenuse AB. So bisector, it's not a good word in English, because bisector or median, is it a good translation? Is bisector the median? Because you know that we have two words in English. One, you can say a median. Median is the line, is this line segment that joins a point to its midpoint. This is not called bisector, that's called a median. And you have also an angle bisector. That bisector is used in an angle bisector, which you divide it in two equal parts, the angle. And then you can also have perpendicular bisector, which is a line that passes through the middle of that and is perpendicular to this one. So, but my impression is that they are using the bisector to be this one. Do you agree with me or not? Do you also have the same impression? Is that right? So we drag a bisector to point D on the hypotenuse AB from a point, yes?
According to Wikipedia, the word they're using is like angle bisector.
Aha. So they are talking about angle bisector, yes? When they drag a bisector, yes?
Yes.
Okay, so that's a little bit different now story. So that's what I'm saying. Usually in English you say angle bisector. Okay, and then perpendicular bisector. Angle bisector is for an angle. So what you say is that, if I understood them correctly, it means that we divide this into two equal pieces,
Yes.
each 45 degrees, and then this is D, if I understood you correctly. So this is 45, 45. Yes? Okay. And then from point D, pull a normal to E on the catheter. I don't understand what is that word. Can you translate what is that? Even I don't know the English. Catheter. Do you know this English word? Is it a Swedish word or not?
Yeah, it's, I don't remember the English word, but it's basically just AC.
Okay, AC. So that means AC. Okay. I don't know that word even in English. So set DE to be D. So what is E then? Pull a normal to point E on. So I don't understand this question. No, normal also means orthogonal or perpendicular, if the Swedish word is similar to English word. So for perpendicular, this is the more common word we use, perpendicular. Another terminology is orthogonal. Another terminology is normal. But I really don't know if they mean normal. Where is E then? Can you help me to find E? Pull a normal to point E on this, just it, yes? And DE is, so I don't know. Might be I should pause recording and then if I understand then we can record. Okay, so let us try to understand this problem. Just wait a little bit. Fortunately, this curtain is not working, so I cannot make it darker. We have to forget about it, but I think it's a little bit feasible at least. So, if I want to draw a right angle triangle as I did before, so for example, let me do it the other way around because it is easier now, okay? So I will take a right angle triangle here. And forget about the names, by the way. I hope that I'm not confusing you. So this time B is this, this is the B. And then what I'm supposed to do, I am trying to angle bisector here of the angle B. So I go here and find the angle bisector. This is the angle bisector. And then what I do, I draw the angle bisector here. And then what I do, I will find the intersection point between these two. And that is D. That's good. And then I can simply ignore what I have done here. So I just get rid of this show object no. And then I will go to find a line segment. And then I connect this. So this is what we have so far. Sorry, I just did it the other way around. I hope that you are not confused. This is my right angle triangle. So each one of these angles that you see is 45 degrees. And then what was the other point? The other point is, for example, of one of these sides, so that you can just drop a perpendicular line from here to there. So what I can do, I can go here and ask GeoGebra to draw the perpendicular line from D to this side. Oh no, that not side. So what was this side? Can I cheat a little bit? Okay, so I did it from D to AC. Yeah, that is, I have to do it, yes?
Yeah, wouldn't it be D to AB?
D to AB, that's my mistake, yes. So I have to do it from D to AB. So I take this one and then to make it to AB. But that's also, so why I don't see it here in my picture? That's also there, yes. Yeah, that's, anyway, so this is always parallel to the third side, yes?
I just have the picture that they have in the solution and how it looks like.
Yes, no, forget about the solution manual, the joy will spoil actually. So, so
Just for the picture.
okay, but I mean that this automatically this becomes parallel to the third one, because if you drop a perpendicular line, it becomes parallel to the third one. It is inevitable, yes? And then what I do, I will take this one and find the intersection point, and then I can just ignore this, show objects, and then I will just do this. So if I understood this correctly, they are talking to say that, okay, 1 over this length, 1 over dE, is equal to 1 over this length plus 1 over that length, yes? Oh. So that is what I understand. If you have length of ED, by the way, let me calculate. So let me calculate 1 over length of DE. Yes?
The picture here is different. It has a vertical line instead. So not
Okay, so let me pause recording to come and see what. Okay, but let me go here and then do something. So I want to calculate 1 over the length. Let us see what GeoGebra tells us, yes? The length, and then what I would write, how should I write the length of segment if I want to program it, if I understand the syntax correctly, segment, and then you say point. One point is capital D and the other point is capital E. Yes? This is at least what I get as the number, 0. What this one. That is exactly the length of DE. We are supposed to show that this is equal to 1 over, it's really annoying sometimes. I cannot get rid of this. Okay, so now 1 over the length of, okay, the length of segment, the object is segment, the sides, yes, segment, yes, the point, and which one is that? AB. So I would write capital A, comma, capital B. And then plus 1 over the length, yes, of what? Of segment, this, so segment, yes, point to point, and that is what? B and C, if I understand it correctly. Yes? Okay, so that is this number. Okay, I subtract D minus E to see what happens. It's 0. So that is correct. So our understanding is correct. Yes, I calculated 1 over that length plus 1 over that length. I got this number. I calculate the length of DE, the reciprocal. And according to GeoGebra, the difference between these two numbers is exactly equal to 0. So our understanding is correct. And the point is that how we can prove this in all cases. By the way, the interesting thing is by construction, hopefully when I start changing this, yes, it will change, by the way. You see, when this angle is no longer 90, the deviation is not 0. But as far as I make this angle 90, it becomes 0, irrespective, regardless of the size, you see. It's always 0. But when I deviate from 90 degrees, this J value deviates from 0. So this is only working for right angle triangles, not any other triangles. But we want to show that this is not a coincidence and this is always true. the interesting part comes in right now. We have to think about why this problem is correct. Okay. Okay. So I would say that okay. I want you to think about the problem yourself as well before I solve it for you. Okay. I even don't know. I haven't checked this before, that I can solve the problem or not. But I don't think it should be hard. But let us try to think. Do you have any opinion how to prove this? So everything we have done apparently is correct. We have a right angle triangle. This is the angle bisector as Buell told me correctly. And then from this one I draw a perpendicular line which is called the normal line to this side, and wherever it intersects I call it E. I assume this length is D. I assume this length is A and this length is B. It's a very nice property. I want to show that 1 over this length is equal to 1 over that length plus 1 over this length. It's a very nice problem, I think. That's my impression. I don't know, how do you think? Okay, do you have any idea? This question is related to this lesson. Probably it somehow should be related to a similarity or something like that. First of all, do you see any similar triangles involved here? Can you tell me which? Because first of all, you need to convince yourself about similarity of triangles. And then when you yourself are convinced, you need to defend it. So why do you say that they are similar? Which part is that? Yes, that's good. This is this part that in principle, we should be able to solve it. So do you think, for example, the first thing that comes to my mind, I'm not completely sure, I think this triangle here that you see is similar to the original triangle. Why is that? Yes, Sergey?
Because the EAD triangle has the 90-degree angle the same as.
So this is 90, this is 90. So one angle from this and one angle from the bigger, one match. Okay, but it is not enough.
The angle A is the same.
Yes, angle A here is actually the same angle A for the bigger one. So yes, at least I am sure that these two triangles are similar. I'm just doing a scratch work. Okay, so at least we know that these are two similar triangles. Then what can I write, by the way? I can write this length. Can you just tell me what to do? So let me, my advice to you is to write all of them to see which one is necessary. Because there are 3 of them involved. First of all, we cannot guess which one is suitable. So I would recommend you to write all of them. For example, if I write AE from here, if I write ED, and if I write AD, now can you fill up these gaps? So if I write AE from the smaller one, what should I take from the bigger one?
AC.
AC, good. If I take ED from smaller one, what should I take from the bigger one?
CB.
CB, yes. If I take AD, what should I take for the bigger one?
AB.
A. Okay, if you don't mind, momentarily let us ignore this one. Why is that good to ignore the last one? Because I don't know anything about AD. I don't know anything about AB. Okay, so for the time being, ignore that one. But what about AE? Do I know something about AE? Apparently not. Let me write for the time being AE. But what can I write instead of AC? AC is B. So this is good. What can I write for ED? Little d. That's also good. What can I write for CB? A. Yes? So this means that AE, which is missing, now I know it. Yes? I multiply everything by B, so AE becomes B times D divided by A. Do you agree? Yes or no?
Yes.
Okay. So now I know this part. So now what can I do? My claim is that I also know AC. Can you tell me what is AC? Sorry, what is EC? My claim is that I also can write something for EC. What and why?
B minus AE.
That is correct. That is correct. On the one hand, you are right. So let me write. On the one hand, hopefully everyone agrees what Ali mentioned is correct. The blue part is this big part, which is B, minus this small part, which is AE, and I know it. Do you agree? On the one hand. But on the other hand, I also know CE from another perspective. My claim is that CE is equal to D. Can you tell me why? Very, very simple, by the way. My picture is bad.
The 45 degrees.
Yeah, she just mentioned that. So it's 45, it's 90, so it's also 45. So it means that this length and that length are equal. So this means CE on the one hand is this. On the other hand, I am also convinced to be D. Yes? And now I am done. I am happy now. So why? Because I move this to the other side, because I want to make D alone. I mean that D is some on the left, everything related to A and B are on the right. So this will motivate me to try to factor D out. So I move this to the other side. D plus B, D over A is equal to B. And then if you see, I can factor a D out from here. And then what is left is 1. What is left here is B over A. And what is on the other side is B. Okay. Then I want to do algebra. So what I do, first of all, do you agree with me? I can write this as 1 over B. 1 plus B over A is 1 over D. Is that easy for you to see that this is correct? So what I did, I divide everything by B times D. When I divide this by BD, D and D are cancelled, B is left. When I divide this by BD, B and B are left, D is left. B and B are cancelled, D is left, yes? And then I multiply 1 over B inside. It becomes 1 over B times 1, which is 1 over B. 1 over B times this one, B and that B are cancelled, 1 over A is left. And on the right hand side I have 1 over D. So we were able to show this. I have a good hunch, actually that was a nice problem actually. So you see it was not trivial at all, but I would consider a double star problem at this level, yes. Because you need to understand, you have to have a good algebra skill and you should also have a good understanding of similarity, yes? So we showed that this independent of the details of the shape is always true. That's fantastic, by the way. We don't measure anything, but we are able to show based on these arguments that these relations should hold. And GeoGebra actually showed that this is correct. Goodbye. Thank you.